有人吗？啊，这个太尴尬了。哎哎，Hello. I think, yeah, I think since it's the first time I do the live, so I don't know how to use the software. I think I turned off the prior live stream accidentally, so now I open this one. I'm not sure whether you can hear me. Okay, maybe it's fine, right? Okay. But I don't know how many people are listening. Hi. Okay, maybe I will just start. Next time I will use OBS. This time I think I just I just turn it off. So I need to open new room. Okay, I will share the screen. This time I use Zoom. So sorry about the inconvenience caused. Okay. Okay. Let me share the screen. Uh, okay. Okay. Maybe I will wait for a while and then start. I think Zoom has an issue because I don't know how many people are in the live room. So I will use my phone to find that. Okay. Okay. Maybe I will just start. Okay. Thank you for coming. Since this is the first time, so I'm also a bit nervous. Okay, hope next time I can improve and do not have the same issue happen. Okay, so first, please subscribe to the channel if you haven't, but I assume you already subscribed. Okay. So in this class, first we will introduce what is disjoint set, and we will then talk about the key concept and the operations. We also will talk about the different implementation strategies. We will show the code and also analyze the time complexity. Since this is not the very basic concept, so we assume you already have some solid foundations in programming. Basically, you should know OOP, and also you should understand what is the array, list, set, and the trees. And also you should understand the recursion. I choose this topic because I think I like this data structure. So I use it as the first class, but I think in the following class, I will maybe return to some basic data structures. Okay. So the learning objective is by the end of this section, you should be able to define what is the disjoint set, and you should be able to explain the operations of disjoint set. And although we will talk about multiple implementations, I think it would be sufficient if you know how to implement the current optimal strategy with the disjoint set. And also you should be able to analyze the time complexity. Okay, so the agenda today, let's first move to the introduction of disjoint sets. To help us understand this concept, if you are new to this concept, let's assume in the real world, we have two groups. Probably that it can be in your classroom or in your company. There are two groups of people. And we find that there is a star. I have a star for one person in each group. It actually means this person could be the representative in that group. So basically, we are using one person to represent the whole group. So that's what it means. One group has one representative. So if we want to know any person like this person, which group it belongs to, we can just use this person, this representative to show which group the person belongs to. So that's the idea. Okay. So suppose now there is a common goal comes. So these two groups decided to merge together to become a larger group like this. So all the people go to the bigger group, and now we find that there is only one person is the representative. So the two options we see here actually compose the disjoint set data structure. So the first part actually usually called find. So we look up the set containing X. X could be the person here. So we return its representative is this person. The second operation here would be union. So we want to union these two sets. So basically it's like if we want to union this person and this person, actually we need to union both sets. So because each person belongs to one set, if we want to merge these two persons, the only thing we can do is to merge these two whole sets. So what we do is look up the set containing X, like this step, and then the set containing Y, so this person, and then we're combining these two sets. As mentioned earlier, we'll pick one representative for this new set. Okay, so I will pause here. I wonder whether there is any question in terms of these two operations, like the metaphor, the two groups in real life, union and find. Okay, I will check the chat. Okay. Okay, so there is no questions. Okay, is there any questions? I'm not sure how to see the chats. Seems no. Okay. Okay, no question in terms of this concept. Okay, how long do you plan this section? Actually, just maybe half an hour to 45 minutes. Depends on whether there is some interaction with the audience. If there is no interaction, I think, yeah, interaction, I think it's just half an hour. Okay, I will just move on. Just now we have defined two operations, find a union, but we didn't decide how to implement them. So we can actually write an interface if you are familiar with Java. So we can define such an interface, but this interface needs to have these two methods, find a union. Let's think about how to implement a class. Oh, okay, sorry, I forget this. I added that. So I think I also need to mention disjoint sets are very useful because they are kind of fundamental concept in computer science. I would say the most useful part would be the minimum spanning tree algorithm. So I think after this section, you can try to look for this algorithm. It's just add a little bit of sorting about the edges. And also, if you want to check whether undirected and unweighted graph, whether it has cycle inside, you can also use this data structure. So they are very useful. And also, it can be used in other applications, but I just mentioned one image segmentation here. There are many more applications. Okay, so for simplicity, we just use integers instead of arbitrary data because in the price slides, we have used like the person here. But to make it simpler, we just use integer. So we convert the image like this. So now we have the integer here. Now we think how to implement it. maybe you can think about how to implement it based on our prior knowledge. Like we need to have one person as the representative, and also we have a set which belong to the same group. I'm not sure what you like. What's in your mind? Like, what is the brute force way to represent these two options? Okay, okay. Uh, so do you have any idea? But actually, this part I can just go on. I think probably in your mind, at least to me, the most straightforward way would be use a map. Because why we can think of using a map is because we have the key serve as the representative, and in each set we have multiple integers. So intuitively, what I think is a map, and like this. Hope you agree with me. So initially, each person or each integer belongs to its own set. So that's why the key and the key is the only element in the set as well. So this actually means each person belongs to its own set. And then if we want to do the union, we want to union 1 and 2. So we just arbitrarily choose one item as the key. So this way I choose 2. So currently we don't have like a heuristic rule to decide which person or which integer would be the key. So I just choose 2 here. So similarly, when we union 0 and 4, this one and this one, I also arbitrarily choose 0, but you can use 4 if you wish, because as I mentioned earlier, we don't currently have a heuristic rule. So when we do union 1 and 3, we just have the same strategy. So 3 and 1, 2, 3 in the same set, so on and so forth. So until last step, we union 2 and 5, we have one whole set like this. So let's think about what is the bad thing about this implementation. It's very intuitive and straightforward. So like, what would be the downside of this implementation? Okay, so I think like you can type in the chat if you are thinking about this issue, but I don't see any like response for this. Okay, so I just move forward. So the downside is that recall there are 2 operations. The other operation is find. So if we want to find which set containing that item, it would take big O n time. Like if it's just like this, we want to figure out which set containing 4. So we need like go to the first set, check whether 4 is inside. And then we go to the second set, we check whether 4 is inside. So we need to iterate the whole keys. And when we have the key, we go to the corresponding set to see whether it is inside. So you may think of, oh, this is the same, because when we union, we need to look for we need to first perform the find. So the union is actually restricted by the find time complexity. So it's big O(n). So you may think maybe we can use another map to record which set this integer belong to. So what I mean here is that for this set, we can have a map. So we say that the key is 0 and the value is 0, which means 0 belongs to set 0. And for this one, we have the key equal to 1 and the set and the value equal to 0 means 1 belongs to set 0. So we can do that. But then it is the downside is that it is very complicated. So we try to figure out whether there is a simpler implementation. Okay. So if you think more clearly, like think more deeply, we have the map to record which value belongs to, the value belongs to which set is just an integer. And if this integer, just like this example, it has limited scope, we can actually use array. So let's move to second part. It is called a quick find. So we can implementing it with arrays. So basically we have array here, and the index we cannot change, but the value we can change. We use the value to representing which set it belongs to. So at the very beginning, the value would be 0 to 5. It actually means the same, the example we see earlier. So this like index 3 here, the value is 3, means the integer 3 belongs to set 3. So when we union index 1 and 2, we try to union these two items. So we should change their value to the same set number. So we arbitrarily choose 2 here. So this is what we see earlier when we use the map implementation. So here we have the key equal to 2. The value is 1 and 2. We see another example. If we want to union 0 and 4, so basically we should update this value to the same value, right? So it's 0. This time, basically we have moved 0 and 4 to the same set, and the key here is 0. So on and so forth, we can do the same thing if we want to union 1 and 3. So we should update the value to these 3 values to the same integer. So here it's 3. And this is union 2 and 4. This is union 2 and 5. Okay, so is there any question here? I believe this kind of easy to understand, right? Okay, so okay, I see a question. Union XY means X merged into Y or Y merged into X. So it's a very good question. So for now, we actually do not have a specific order. So it's just arbitrarily choose the set. So basically, if you want to merge 1 and 2, you can put all the value as integer 2. You can also put all the value as 1. It essentially means they belong to the same set, but currently we don't have the strategy to decide who will become the new set value. Okay? Okay. Okay, let's see the code, the implementation. So we call this quick find disjoint set class. So it implements the interface we see earlier, disjoint set. So here is a constructor. So basically we need to iterate all the n here. And then initially each person or each integer is its own root. The root actually means the final representative, like the automator representative. So it's itself. And we have two methods. One is find. So find, since we are using the root array, so the find actually is root the value. X is like the index. So this is pretty fast. It's big O1. So that's why this implementation is called a quick find. How about the union? Like recall what we do in union two groups in real life. We need to first find their representative. So that's why we first do the find. So we have X root and and Y root. Only when they are not come from the same group, we do this union or merge. So we should first decide whether they are equal to each other. So if they are not equal to each other, we will need to update all the values equal to X root to Y root. Okay, okay. So is there any question in this quick find implementation? Okay, so okay, seems no questions. I will move on. So let's analyze the worst case runtime complexity. So the constructor for sure is big O(n) because we need to iterate all the items from 0 to n-1. The find is big O1, and the union in the worst case since we need to update all the items belong to set X to set Y. So in the worst case, we need to change all the values. So it's a big O-N. Okay. Okay. So this is the worst runtime analysis for quick find. But as we mentioned earlier, union is slow because the time complexity can become big O-N. So like if we want to merge this to this, I use a tree structure here. It actually means sometimes it's actually just similar to the two, like the group example we saw earlier. It seems like not everyone is directly linked to 0. But if you wish, you can just make a 4 direct to 0. That's also fine. It just show some. It just shows. How do I say? I think it doesn't matter too much for now. So you can also link the 5 to 0. It doesn't matter because essentially each set only have one representative. So if we want to merge this to this, what we do is that because previously all the items like 7 and 8, their representative value is 6. So it's 6. So if we want to merge this to this, we should actually change all the 6 to 0, right? That's what we should do. So we add a link here. We actually update it to 0. Okay, I actually prepare like an activity here. Like, can you think? But no, I don't think we can pair the audience here. So maybe you can think for a while, like, can we only change one value when we do this union? Okay, maybe just 30 seconds. Can you think of the way we only need to change one value when doing the union? If you have think of the solution, you can type 1 in the chat so that I will ask you to give you more time to type the solution. Otherwise, I will just move forward. Okay. So yeah, we change the root of 6. Yes, that's correct. But I think you also need more modifications. So if you just change the root of 6 to 0, it works. But you still remember that the 7 and 8 has the root value of 6, right? So that means we actually need to change the root to parent. It goes to quick union. So basically, we tracking the parent instead of root. So what does it mean? So this time, the value here means the parent instead of the root, the final representative. So basically, for 0 and this 1, 2, 3, their parent would be 0 because they are linked to this 0. But for 4 and 5, they link to 1 and 2, right? So we just write it 1 and 2 here. And for this small tree, they all link to 6. So it's 6 here. There is 2 things we need to notice here. One thing is that the one set only have one representative. This is the final representative. We call it a root. So this tree, the root is 0. For this tree, the root is 6. This is the one thing you need to notice. Another thing you need to notice is that another thing you need to notice that okay, I think this thing has skipped my mind. Okay, I will go back to it if it comes to my mind again. Okay, so that's the thing. So if we want to make this small tree to the big tree as this like audience mentioned, we can just change the parent value of this 6 to 0. So that's how we just need to change one value. Okay. So we already have this implementation. Let's write the code. So this time the code quick union disjoint set. Sorry, there is a typo. I didn't notice before. This is a quick union disjoint set because the last implementation is quick find. This is the quick union. So we need to update this array name from root to parent, but the initialization is the same. So the constructor is the same, but just change the name. And for the find, what we do is that we need to find the final representative. As I mentioned earlier, the one set only have one representative, and this representative, because this representative does not have a representative, so it is its own parent. So when we have one index, we should go up to find that root. So the condition is that root equal to itself, the parent value equal to itself. So that's how it implements. For the union, since now we only change one value, so we have update the previous is a few lines. We need to do a for loop inside, but now we just need the parent x root equal to y root. Okay, so for this part, is there any questions for this implementation called a quick union disjoint set? Okay, so is there any questions? Okay. I feel the YouTube chat is still not that it's not that active, so okay, so it still sounds like I'm talking to myself. Okay, but the issue is the tree can be very tall as well. For instance, if we want to union 0 and 1, if we always make the second node as a new root, so when we union 0 and 1, we make 1 to be the root. And if we want to union 1 and 2, we also make 2 as a new root. So on and so forth. When we want to union this tree and the single node 3, we also make 3 the new root. So we will have like a list style tree. So the tree can be very tall. The worst case, the height would be bigger n, or would be n, right? What will be? Yes, that's a good question. So like you can see, the height could be n. So when we try to find something like, or we want to union something like, in the worst case, you need like we want to, if we want to find the root of 0, we need to climb this whole tree. So it would be n. So the worst case, the runtime analysis would be bigger O n because like the case we see earlier. So if it's just like a list, so it would be climbing the whole tree. Okay, indeed. Yes, you have figured out this is O bigger O n time complexity. Okay. So here is a quiz, but I'm not sure how many people would take a part in. So the quiz that I plan here is that in the quick union implementation, if we change this line to parent x equal to y root, is that still correct? So this is what we implement before. So because we need to first find their root, and also we change the parent x root to y root. So if we change it using this line, will it still be correct? Okay. Okay, so can you like take part in and type your answer in the chat, like yes or no? Yes. Okay. Actually, okay, thank you for the participation. The answer is no. Why? Why is no? Let's see an example. So this is the question lines. So the line has been updated to this one. I think, yeah. So parent x equal to y root. Y is wrong. We can just see this example. So basically, we want to union 7 and 5. Okay, if we want to union these two. So the x root, the root of 7 would be 6, right? And the root of y would be 0. And if we use this line, is actually means parent 7, because recall x is equal to 7, right? So we run this line would be parent 7 equal to 0, right? So basically we just link this to 0. It's certainly not right because it did not actually merge these two sets. It only merged this item to the other set. This 6 and 8 would be left out. Okay? I think it's clear now, right? You understand it's not correct because it did not actually do the merge stuff. Okay, I think I feel anyway. Okay, so I think we can move on now. Okay, let's think about this question. Like, assume we want to union 5 and 7 again. Which one is a better choice? The first choice is that we change the parent of 6 to 0. So we link the three nodes to the big tree, or we link the big tree to the small tree. Like we change the parent 0 to 6. Which one is better? Okay, so which one is better? You can type your answer in the chat. So if like which one you can say up or down, like which one is, or top and down, which one is better in your mind, or it doesn't matter. Yeah, I see. Okay. Okay, or it doesn't matter. Anyway, I think no one is okay. The first one, small to big. Yes. Why is small to big? I think it's also like be constant to our intuition. Why it's the case? Let's go to the next implementation called weighted quick union. Okay, so what does this weighted quick union means is that we track the size of the tree, and we always link the small tree to the big trees. So yes. I think the balance is not a very good term here, but I can see what you mean. It's actually, we want to make the tree more like shorter. We don't want it to be tall, right? Because recall previously, when we try to get the root, we need to climb the whole tree, which could be the length of n, right? So that's why we want the tree to be shorter instead of taller, right? So you may see there is two implementations about that. One is tracking the size like we do. Another one is you can see you would call union by rank. So basically it would +1 instead of plus the size of the other tree. So let's see the implementation like I mentioned earlier. So we have a size. This is a very simple way because for the size, every time you merge two sets, you can just accumulate the other set's size to the new set. So this is a very simple way. So as I mentioned, the alternative implementation is +1. It's called union by rank. And also you are wondering if I want to maintain the height, is actually similar to maintain by size. Because if you think more carefully, as long as we make sure every time we attach the small tree to the bigger tree, we can always get as short a tree as possible. We will not get like the least style tree. Yes, indeed. Okay. I think that's the case. If you don't believe it, you can think of, you can just try some small examples like if you want to, there is one tree with 2 nodes, the other tree with 1 node. Since we only attach the small to the bigger one, so we will not have the single line tree. Okay, and this is pretty simple. But the thing is, like, even we do that, this tree can be very tall as well. Why? Because, for instance, at the beginning, there are 2 separate nodes, 0 and 1. And we need to union them. There's no other way, right? That's the only way. Say we have another 2 node tree, like 2 and 3. They are the same height and the same size. So we cannot do anything. If we want to merge them, that's the best we can do, right? So let's say we get the same tree. It's also 4 nodes. That's also the best we can get. And we need to union them. So the current height is already 3. And the number of nodes here is 8. So let's say we have another 8 nodes, just like what we have earlier, the same here. So we need to union them. Then the height of this tree is already 4. So if you see this number frequently, you will understand this is actually log n, right? Okay. So the worst case, the height is log n. So we can get the runtime analysis here. So the find is a big O log n, and the union is the same. So it's in practice already pretty fast. So this part, I think you all understand, right? Like why it's log n. This weighted union, weighted quick union, and we use the size array. Okay. But we can do better. So that's why we go to the final part, is weighted quick union with path compression. So what we do here is when we do the find operation, we tie all the nodes C into the root. Suppose here this is the 4 nodes tree we see earlier, right? So if we do find 3, we need to go up, right? 3, go to 2, and go to 0. And because this 2 is not the final root, we will attach all the roots along the way to the final root. So basically, we will remove this link. We will link 3 to 0. So that's the thing. Okay. Let's see some visualization. I think you can use the link afterwards. Okay. So you can see my screen, right? I think have I shared the screen? No, I'm not sharing. Maybe I should share this one. Okay. How can I share it? Wait a moment. I don't know. I think I'm sharing the PPT, so it seems how can I update the sharing screen? Maybe I will just skip it. Yeah, probably I will share the link afterwards. You can go to this link. So basically, this link would have visualization of disjoint set by adding the union by rank and the path compression. So you can see more examples if you wish to see how it works. Okay. Okay. Now let's see the implementation. So implementation for this is what we implement quick union. So we go to one item when the item equal to its parent value equal to itself, we stop. So we return X. Now we want to do the path compression. The first part is similar. We need to find the root. And then what we do is we go from this X until the root. If this any root do not equal to root, we will update their parent value to the root. So here is the implementation here. So for now, is there any question? Can you understand this implementation? I think it's pretty straightforward as well, because it can actually be split into 2 parts. First part is finding the root. Second part is updating all the nodes which do not equal to the roots, their parent value to root. So I think it should be easy to understand, right? Okay. Okay, I suppose you all understand since I didn't see any chat messages. Okay, the question is, can we use recursion implementation here? Because this has been split into 2 parts. It seems like a few more lines. Can we write a more elegant recursion implementation? Indeed, the recursive version is much easier to understand. Yes. But I don't know whether you can think of the recursive implementation by yourself. So I believe because we need to find the X equal to its parent x. So if x does not equal to parent x, we need to keep finding, right? And at the same time, we need to update the parent value. So how it implements. Okay. So I hope you can think of this implementation by yourself. I think it's more elegant and simple to understand. The question here is that related to this recursion. Okay, the second quiz. So in this weighted quick union with path compression, if we change this highlighted line to return x, is it still correct? Okay, please reply your response in the chat. I will see your participation. You can reply yes or no. So basically, this is how we implement the path compression in the find method. And in the recursive implementation, we said it should return parent x. So if we just return x, is that still correct? Yes, one person said no. How about the other person? What is your opinion? Like, is that yes or no? Okay. Okay. Anyway, I think no one will participate. Okay. So yes, the answer is no. So you are correct. So why is no? Here is another visualization, but this website is used to show, like, given a Java program, it will show the code stack. So you will see when you go to each line, what is the current code frame look like? I think this is pretty useful, especially for some recursive or backtracking problem, because someone had maybe sometimes you have difficulty understanding the backtracking or recursion. This is pretty useful. I think you should know this website and use it. But I think it may not necessary for this question, because we can know it's wrong by thinking a simple example. So if we want to union 0, 1 and union 1 and 2. So when we union 0 and 1, like, I think I can do a annotation. Okay, nice. So this one, great. So this is 0 and this is 1. It's arbitrarily choosing. So 0 is the root and 1 is like the other node. So when we want to union 1 and 2, so this is 2. So we need to union them. We need to first do find, right? So the root of 1 is, essentially the root here is 0. So we should link here, right? So basically, the parent should all be 0. Like this 0, 1, 2, their parent should all be 0. That's correct, right? But if you use this line, you run this line, return x, then you will get 2, their root is the parent equal to 1. Why it is the case? Because let's say you still remember how the find works, right? So if you do find 1, I don't think it's simple. I think you can just sorry, I don't think it's very easy to draw the things here, but I think you can just easily run the few lines before you will see what I mean here. So if you print the parent value, it will just give you 0, 0, 1. So it's certainly not correct. Why it is the case? Because like when we do find 2, it should be 2, but when we do find 1, it should be 0. But since when the input is 1, so eventually it would return x. So eventually it would return 1 for the parent of 1. Do you understand the case? No, we need to return root, not the current root. Yes, that's the thing. So if we just return X, it would just return whatever the input here. So it would return 1, but essentially we actually want 0. Okay, so it's I think this part is very easy to make a mistake. So like maybe next time you write the code, if you are unsure whether it's return parent X or X, you can just run this simple example. You don't need to memorize whether it's X or parent X. You can just run this simple example. You will get the correct answer. Okay. How can I remove it? Wait a moment. I will just remove everything. Clear my choice. Okay. So I think this part is also interesting. Like it is actually hard to analyze if you don't know it before, because by using the weighted quick union and the path compression, we are trying everything we can do to make the tree, but it's not the actual tree, but it's just a representation. The tree to be as flat as possible. So what would be the time complexity? This is very long. You can read it afterwards. Essentially, there's a table here. Is actually tell you on average. Notice this is on average. It's not saying a single find or single union have this time complexity. No, it's said on average. So that's why it's called the amortized analysis. So it's like on average. So there is a log star n. What does it mean? It actually means how many times you need to run this like logarithm function to get a value less or equal than 1. Here, table means like for n, this is a very huge number. And even that huge number, the log star n is just 5. So you can say for any realistic or reasonable number, the log star n actually close to a constant. So it's nearly constant, but not essentially constant. So this is very, how do I say? I think it's very unique. I only know it's used here. Actually, it has a tighter upper bound. It's called the inverse Ackermann function. So when we're talking about the time complexity of the implementation with weighted quick union and with path compression, we can either say inverse Ackermann n or log star n, both works. So let's see all the implementation we see today. So suppose we have n items or n integers and m operations, either union or find. So the total runtime for the quick find, certainly it's n times m, right? Because recall previously we analyzed a single operation, the worst case time complexity, right? And for quick union, it's the same. For weighted quick union, since it is log n, like it's tightened by the height of this tree, so it's m times log n. And what is this n? This n means the constructor. You do the initialization, so certainly you need to iterate all the n. I write n plus m log n here because we are unsure which number is bigger, is that n or m. So that's why I write like here, like this. I think you need to remember the last one because nowadays we just use the final implementation. The preceding 3 implementation are just helping you to understand how can we improve. But I think after this section, you only need to know this one. Okay. Yes, I can share the PPT for sure. Okay. So I think that's all for today's section. So what we learned today is that we know now the current standard way to implement disjoint set, the weighted quick union plus path compression. And we also like see a few different implementations. The first is quick find and also then quick union, weighted quick union and weighted quick union with path compression. Yeah, just mention again, sometimes you will see like union by size, union by rank is essentially the same. It's just a weighted quick union. Okay. And we also know the runtime analysis. Okay, one last part is, if you like, can you give me some like feedback so that I can improve next time? You can scan the QR code here. I remember there is a few questions related to understand how much you learn after this section, but you don't want to share, you can just say NA. I think the last question would be important to me because I want to see in the future, how should I improve? So please take your time to scan this QR code and give me the feedback. But you can also just like give me comments, that also works. Okay, I think I'm not sure if using coding is enough for coding or need to choose. Yes, you need to use both. You need to use both. Okay. I think it's pretty. I think after today's section, you should be very confident to write the code, right? Because you already see the whole iteration of this implementation. So you should be confident to use the optimal implementation. Do not just use one. You should use both. Okay. Okay, that's just a little acknowledgement. So the slides and the quiz got inspirations from the following three resources. The icons are from this website. I think that would be all. Yeah. Okay. Okay, thank you for attending today's section. I think, yeah. Okay, so yeah, I think that would be all. Okay. I'm happy to receive any feedbacks. And this is the first time, sorry about the like changing the live stream resource, like previous live stream have been turned off by me accidentally. Okay. Okay, thank you for your time. I hope you did not waste this like 15 minutes. You actually know how disjoint set works and how to implement them. This is very important. Okay, so I think after this section, please go to LeetCode and look for union find tag and try to solve some questions. You will understand this much better. Okay.